Welcome to the Deep Dive. We're here to break down complex AI research papers, giving you, the busy ML engineer or researcher, the key takeaways without the dense math getting in the way.
Exactly. And today we've got a really interesting one. It's called, What is the Objective of Reasoning with Reinforcement Learning? By Demick Davis and Benjamin Recht. It just came out, October 2025.
And it tackles something pretty fundamental, right? We use RL algorithms all the time for post-training LLMs, things like reinforced, GRPO, rejection sampling, often just with a simple or incorrect reward.
Right. But the question is, what are these algorithms actually optimizing? What's the mathematical objective we're climbing when we run these things? It's often surprisingly opaque.
Okay, so this paper tries to clear that up, and their answer apparently is quite surprising, links things we thought were separate.
It really does. It argues pretty convincingly that many of these popular methods are fundamentally doing the same thing. Okay, let's jump into the short summary first, the key points.
Perfect. Let's do the 1-minute version.
Okay, insight number 1, unification. If you're using binary rewards good, bad, correct, incorrect, then almost all these common RL post-training algorithms, like reinforced, GRPO, rejection sampling, they're basically equivalent.
Equivalent how?
They're all just different flavors of stochastic gradient ascent acting on essentially one single objective function.
Okay, so what is that objective? That's insight 2.
Exactly. The objective they all share is maximizing the probability that the model spits out a correct answer for a given prompt. Let's call that PETA, CXTI. But crucially, they don't maximize that directly. They maximize a monotonically increasing function of that probability. Think of it as stretching or squashing the probability value before optimizing. We'll call that function H.
Monotonically increasing. So as the probability goes up, the function value also goes up, just maybe at a different rate.
Precisely. Higher probability always means a higher objective value.
Got it. And insight 3 tells us why we have different algorithms if they share this core objective.
Yes. The specific algorithm you choose. That just dictates which monotonic function A you end up using.
Yeah.
It determines the shape of that rescaling.
Ah, okay. Examples?
So vanilla reinforce, the simplest one, that uses the identity transform. It just maximizes the raw probability.
Makes sense.
Rejection sampling, the kind where you sample a batch and only use correct answers. That one, maybe surprisingly, induces a function that's really close to the logarithm. So HET behaves like log
That's
T.
interesting. Log transform, okay.
And GRPO, generalized policy optimization, which often gets touted as more advanced, that corresponds to a function close to the arcsine of the square root transform. So the arcsin-Sqrt root.
Okay, that sounds way more complicated than just the probability itself. So what here is, why bother? If they all want the model to be 100% correct eventually, why pick the complicated function?
That's exactly the point the paper makes. Choosing between reinforce, RS, or GRPO isn't like choosing fundamentally different goals. It's more like choosing between, say, hinge loss and log loss when you're doing standard classification.
Ah, okay. So it's about the shape of the loss landscape, how it guides the optimization process, maybe how stable it is or how quickly it converges.
Precisely. You're picking a monotonic transformation that might offer better optimization dynamics for your specific task or model. There's no single best one universally. It's likely context dependent.
Okay, that's a fantastic summary. It really reframes how we should think about these algorithms. Let's rewind a bit now and dig into the context. RL for LLMs isn't quite the same as RL in, say, robotics or games.
Absolutely. We need to be clear. We're not usually talking about complex tree search or an agent exploring a world here. In LLM post-training, RL is primarily a tool for fine-tuning the model's parameters based on some external feedback signal.
Like aligning it with human preferences or making it better at specific tasks like math problems where you can get that correct label.
Exactly. It's about adjusting the weights based on often sparse feedback.
The paper lays out a kind of general meta-algorithm for this. 4 steps.
Yeah, it's pretty straightforward conceptually. Step 1, sample some prompts, $6. Step 2, have the model generate responses. Step 3, get labels from somewhere human, another model, a checker, saying if it's good or bad for $6.
Correct, basically.
Right. And step 4, use those prompt response label sets to fine-tune the model. And it's in this fine-tuning step where all the different RL algorithms slot in and where the paper's unification insight applies.
But hang on, there's a really important caveat they mention, a kind of prerequisite for this whole process to even work.
Yes, this is crucial. You might have the fanciest policy gradient algorithm, but the paper emphasizes that it only works if the model or your sampling process can actually generate correct answers sometimes.
So if the base model is just terrible at the task and never stumbles upon a correct answer,
then the RL algorithm has no positive examples to learn from. It gets no signal indicating the right direction. The gradient calculation relies on seeing those successes.
Right, so you can't just take a completely clueless model and expect RL fine-tuning alone to magically teach it a complex skill from scratch using only binary rewards. It needs some initial capability.
Exactly. It highlights that RL here is more about refining or amplifying an existing, perhaps weak ability, rather than discovering it wholesale purely from binary feedback. You need those successful samples.
Okay, that's a very important practical point. Let's get back to their unified objective. They write it as maximizing z-status. Can we explain that without making everyone's eyes glaze over?
Let's try. So t-data just represents the model's parameters. T-data is basically the average score the model gets across all possible prompts, according to some distribution of tellers.
And the score for a single prompt, $6, depends on call CX, the probability the model gives a correct answer for that specific prompt.
Yes. But instead of just averaging that probability p-dollar, we average Wayne PD, where one of the vollers is that monotonically increasing function we talked about.
So $, is like a lens or a filter we apply to the probability before we average it.
That's a good way to put it. If dollars to logs, we're just averaging the raw probability.
Yeah.
If averaging the log probability, which, heavily penalizes low probabilities, the choice of dollars shapes how we value different levels of correctness probability.
Okay, makes sense. Now, how does this connect back to the algorithms we actually use, like standard supervised learning or reinforce?
Well, think about standard supervised learning, SL. You have correct examples, and you usually maximize the sum of the log probabilities, log peta. The gradient for that is just novel theta.
Right, the standard gradient used in training language models.
Now, reinforce, Williams's classic algorithm, gives an unbiased estimate for the gradient of any objective function that depends on samples from the model of peta. The estimate is novel theta and alpha theta.
So you take the standard SL gradient and multiply it by the reward or score FZ.
Exactly. Now, in practical LLM fine-tuning, we often see a slightly more concrete version, like algorithm 1 in the paper. You sample a batch of mildly-reached responses for a prompt 6, get your labels, and then update the parameters using an average.
And the update involves that SL gradient, double log pi theta, but it's multiplied by some weight, Z also.
Oh, yes. The little log tero theta plus eto frac 1 pk. And these weights, Zillow, often called advantages, are usually motivated as a way to reduce the variance of the gradient estimate, make training more stable.
But that's where this paper throws a curveball, right? They're saying the Zillow weights aren't just for variance reduction.
That's the core argument. They show that the specific choice of how you calculate these weights, Zillow, fundamentally determines the shape of that implicit objective function annullers. The weights induce the objective.
So the weights aren't just a practical trick. They're the design choice defining what you're actually optimizing.
Precisely. It flips the perspective. For example, consider the simplest version of reinforce for binary rewards. You set $0 to be just 1 if the answer your dollars is correct, and 0 if it's incorrect.
The indicator function.
Right. And if you plug that specific $0 into the math, it turns out you are exactly performing stochastic gradient ascent on the objective JT dollar. You're maximizing the raw average probability of correctness.
So the simplest weighting scheme leads to the simplest objective. Makes sense.
And they go further. They define a whole family of weighting schemes where $0 depends linearly on the reward, or 1, and also on how many other samples in the batch were correct. It sounds a bit complicated.
It does involve something called the regularized incomplete beta function, which sounds pretty intimidating.
It does. But the high-level takeaway is that this mathematical structure connects a wide range of reasonable weighting schemes directly back to inducing a specific dollar function. The number of successes you see in your batch and how you weight success versus failure sculpts the dollar function.
Okay, so we can, in theory, design weights to get specific objective shapes. Let's look at the shapes we get from algorithms people are actually using. What about rejection sampling?
All right, RS. A common way people do it is sample, say, Mahler answers for a prompt. If none of them are correct, you just skip the update for that prompt entirely.
Right, throw away the batch.
If you do get some correct answers, you calculate the gradients only for the correct ones and average those to make your update. You ignore the gradients from the incorrect samples.
Intuitively, that feels like it should also just maximize the probability, maybe more efficiently, by focusing on successes.
That's what you might think. But the paper shows that the act of skipping batches with 0 successes introduces a subtle but important change. It means you're conditioning on not having 0 successes.
Ah, okay. And that changes the effective objective.
It does. They show that this standard RS procedure induces an objective function, 1 HMT$, that closely approximates the logarithm. As your batch size gets larger, the approximation gets better. Figure 2 in the paper shows this convergence quite clearly.
Wow. So just by implementing that simple rejection rule, you're implicitly optimizing something closer to log likelihood than raw probability. Why would that be potentially good?
Well, think about log loss in classification.
Mm-hmm.
Logarithms heavily penalize very small probabilities. If piece x is tiny, like 0, 0, 1, is a large negative number, this gives a stronger push away from really bad predictions.
So it might help the model learn more quickly when it's not very good yet, and maybe distribute probability mass more effectively, like standard maximum likelihood estimation.
That's the intuition. It focuses effort on not being terribly wrong. They also mention an alternative RS algorithm where you keep sampling until you get a fixed number, say Bayer dollars, of correct responses. That version exactly optimizes the log objective, GRPO, without approximation.
Okay, interesting. So RS leans towards log probability. Now, what about the more complex one, GRPO, generalized policy optimization? That involves variance normalization, right?
Yes, GRPO stands out because its gradient estimator, equation 6.1 in the paper, takes the sampled reward-weighted gradient, but then it divides it by the square root of the variance of the rewards received in the batch, plus a small epsilon for stability.
Dividing by variance, or standard deviation, rather. Why do that?
The usual motivation is again related to optimization dynamics. If the model is very certain, low variance in rewards, either all correct or all incorrect, the standard deviation is small, so you divide by a small number, amplifying the update. If it's uncertain, high variance mix of correct and incorrect, you divide by a larger number, damping the update. It tries to adapt the step size.
Okay, adaptive step size makes sense, but how does that relate back to one of these H functions? It seems much less direct than the weighting and reinforce or the selection in RS.
It's definitely less obvious. The way they connect it is by looking at the idealized gradient structure. If you imagine having infinite samples and no regularization, epsilon to null, what does the gradient of GRPO need to look like to match the structure GRPO imposes?
And what's the answer?
The gradient of GRPO structure after normalization effectively makes the gradient proportional to nebula theta p.
Okay.
So the question becomes, what function dollar has a derivative pito that's proportional to $1 squaring pito?
Ah, calculus flashbacks. And the answer is?
The answer is proportional to $2 arcsin, the arcsin of the square root transform.
Incredible. So that complex-looking variance normalization in GRPO is, in the ideal case, just implementing gradient ascent on an objective scaled by the Arcsin-Sqrt function.
Exactly. And figure 3 in their paper shows how the actual dollar function induced by GRPO with finite null and non-zero epsilon approximates this arcsin shape and becomes closer to the identity ni-tt as the regularization epsilon increases.
Why might the Arcsin transform be useful? Does it also have nice properties like the log transform?
It does. The Arcsin-Sqrt transformation is known in statistics as a variance stabilizing transformation for binomial proportions, like our probability dollars. Applying it makes the variance of the transform variable less dependent on the mean probability itself.
So by optimizing this transformed objective, GRPO is trying to work in a space where the noise level or variance is more uniform across different levels of correctness probability.
That's the idea. It's trying to make the optimization landscape smoother or more predictable in terms of gradient variance, which could potentially lead to more stable and faster convergence, especially in deep learning contexts.
Okay, let's pull this all together. We have this overarching idea, the monotonic rescaling principle. Reinforce is ROG-T. Rejection sampling is roughly arctels. GRPO is roughly arcsin.
And the key is that these aren't fundamentally different goals in terms of where they want the model to end up 100% correct, but they represent different paths or different ways of shaping the journey towards that goal.
And the framework is actually constructive, right? Section 7 talks about how you can use this understanding to design new methods.
Absolutely. Because they show the induced weight to function relates to a mathematical object called a Bernstein polynomial, which is defined by those weights in Ham-Malls, weights for correct samples given several successes.
Meaning, if I want a specific target shape for RLOAs, I can work backwards to figure out the as and dollar weights I need to use in my RL update.
Oh, Butch. I give an example. What if you use the variance itself for normalization instead of the standard deviation like GRPO? That corresponds to a different set of weights, and it induces a function close to the log odds, or logit function, log T1T.
So researchers now have this toolkit. They can explicitly choose the shape of the objective landscape they want to climb based on what they think will work best for their problem and engineer the weights accordingly.
Exactly. It moves the focus from just picking an algorithm off the shelf to intentionally designing the optimization objective's shape.
But then there's the theoretical reality check they bring up again near the end. If the model is powerful enough.
And if you could actually run the optimization until you reach the global optimum.
Then the choice of dollars doesn't actually matter for the final result.
Theoretically, no. Since all these Euler functions are monotonically increasing, the point that maximizes the dollar is the same point that maximizes dollar self, which is when per p in t 1, meaning the model assigns 100% probability to correct answers wherever possible.
So have we been kidding ourselves thinking GRPO is somehow inherently better than reinforced just because the algorithm looks more complex?
The paper suggests we might have been focusing on the wrong thing. The difference isn't necessarily about achieving a better final outcome, assuming we reach the optimum. This leads back to their great analogy.
The hinge loss versus log loss comparison?
Right. In classification, both aim to separate the classes correctly. They just penalize errors differently along the way. Choosing between them often comes down to computational properties, sensitivity to outliers, maybe margin maximization intuitions. But statistically, they often yield very similar classifiers.
So arguing GRPO versus reinforced might be like that. Both push towards correctness. The difference lies in how they push the dynamics of the optimization process.
Exactly. The best choice of monotonic rescaling identity, log, Arcsin, logit, or something else, is likely task-dependent, model-dependent, data-dependent. It's about finding the shape that leads to the most efficient and stable convergence in practice.
Which leaves us with that final provocative thought, the real question this paper opens up for future work.
If the theoretical optimum is the same, then the only practical reason to prefer log over the simple dollars must be their effect on the optimization dynamics.
How fast do they converge? How stable are they across different kinds of prompts or different model architectures? Does the variance stabilization of Arcsin actually translate to faster wall clock training time on large, diverse data sets compared to the simplicity of reinforce?
That's the million-dollar question now, isn't it? This paper provides the theoretical framework, showing they're all related transformations of the same basic goal. The next step is rigorous empirical investigation into the practical trade-offs of these different landscape shapings.
What are the convergence rates, the stability properties, the sample efficiency trade-offs in real-world LLM fine-tuning scenarios?
That's where the research needs to go next. This paper gives us the conceptual clarity to ask those empirical questions much more precisely.
A really clarifying piece of work, then. It takes a potentially confusing landscape of algorithms and provides a unifying mathematical perspective.
Definitely. It helps us move beyond just algorithm names and think more deeply about the shape of the objective we're actually asking our models to climb.
Fantastic. Well, that's all we have time for on this deep dive into Davis and Rex's paper. We hope this breakdown helps clarify what's going on under the hood in your RL fine-tuning work. Thanks for joining us.
See you next time.